This is Mr. Sand coming back at you. This is specific heat that we're talking about now. Specific heat. Well, I want you to think about before you even get started, why does something like white toast burn so easily and wheat toast doesn't? You can put it in your toaster. You can try this at home. It's a little test. You can see that if you put in white toast for the same amount of time and exposing it to the same amount of heat as wheat toast, white toast will burn. It burns crazy. And then if you take out toast after it's done, you'll notice that white toast loses its heat very quickly. The temperature drops like crazy. You get cold toast right away with white toast. But wheat toast stays nice and warm for a long time. The reason behind this is something called specific heat. Specific heat is something that, well, you might have thought of this before, but maybe you haven't really told it to yourself here. You haven't articulated it to yourself here yet. But it's the idea that substances accept and give off energy differently depending on their substance. So it's the amount. So I'll just define it right here. Specific heat. Specific heat is, for every object, it is this. It is the amount of energy added to material to raise it 1 degree Kelvin, or I guess you could call that centigrade if you wanted to raise 1 degree Kelvin, raise what 1 degree Kelvin? Raise 1 kilogram of a substance, of the material, 1 degree Kelvin. That's it. So here's a way in which we write a little formula for it. Specific heat, the abbreviation for it is C, uppercase C. So our little equation for it is Q equals MC delta T. I call this Q equals MCAT because it looks like MCAT, but this is delta T here. So this right here is the mass of the object that you're considering. This is the specific heat, and it's a different value, specific heat of substance, of whatever substance you're discussing, of substance. And this delta T is T final minus T initial. So it's the final temperature minus the initial temperature. Since we're doing a difference in temperatures, it doesn't matter that we use Celsius here, but get in the habit, please, of using Kelvin every time you use any kind of thermal calculation. And of course, Q is heat. That's heat right there. All right. Specific heat is given in the units. It's either given in the units joules per gram times degree Kelvin, or it's given in kilojoules per kilogram degree Kelvin. When we say degree Kelvin, it also means degree Celsius, so they're interchangeable. You don't have to have degree Kelvin. It's the same thing as degree Celsius. Just to let you know. Okay, so now I want to talk a little bit about an equation. I want to talk about this equation. We can manipulate it using the idea of thermal equilibrium. So remember, the thermal equilibrium was when two substances exchanged heat at the same rate. So you could say that the change in the energy of one of the objects, let's call it the first object. Let's have two objects right next to each other. Here's this object, and then let's put not a red one, let's put a pink one right next to it. This plus the change in the energy for this. When those changes equal 0, we're in business. We're in thermal equilibrium. So that means the change here is the same as the change there. Okay? Does that make sense? It should. Let me see if I can zoom out. I want to zoom out. Please let me zoom out. Zoom. Ah, not there. Shoot. Just let me zoom out. That's all I'm asking. It's not that hard. Why did you zoom in the first place? I don't know. Frustrating. Anyway, we can make it work. Don't worry. Okay. So, great. Big deal. Let's just change these. The delta E for each one of these is really going to be the heat for this object. So it's going to be Q. So Q in this case is going to equal the change in the energy between these two objects. So since Q is just going to be it's just going to be Q plus, so it'll be Q for one, and it'll be Q for 2 will equal 0. Well, then what we can say is that this just equals MCAT, and this one for being for the second object. So it's a mass of 2, a specific heat of 2, and the change in temperature of 2. So equals 0. And the Q for 1 will be the mass of 1 plus the specific heat of 1 times the delta T of 1. Great. Now we'll just expand this a little bit more. I'm going to expand the delta T's out here. So it'll be M1 C1 times TF of 1 minus T initial of 1 plus, and now I'm going to use the other object, be the mass of 2, the specific heat of 2 times TF final of 2 minus TI 2, and this whole thing will equal 0. All right. Now, what we can do now, we can do something really cool. We can notice that the final temperature, since this is in a thermal equilibrium, these two will equal the same thing. So we don't even need to have a TF of 1 or TF of 2. Right? So we can just cross off this right here because it's going to just be final temperature. That gets us like terms here. Now we can do some algebra with that. But guess what I'm going to do? I'm going to skip a couple algebraic steps. I'm just going to show you the very final step. When you rearrange all of this stuff, you can try it for yourself. It's a fun little exercise. TF is going to equal the mass of object 1, so it'll be M1 times specific heat of object 1 times the initial temperature of 1 plus the mass of 2, specific heat of 2, initial temperature of 2. And this whole thing is going to be over, let me go back to the blue. All right, it'll be the mass of 1 times the specific heat of 1 plus the mass of 2 times the specific heat of 2. Okay. This is very useful when we're using something called a Baum calorimeter. And you'll see that in the problems. Right. So let's go on to some warm-up problems. Let's get a new page right here. Real quick. It'll be like super quick. I think we've got a few minutes left. Right. So let's see here. Warm-up problem number 1. We'll do the first two warm-up problems. Warm-up problem number 1. When you turn on the hot water to wash dishes, the water pipes have to heat up. How much heat is absorbed by the copper water pipe with a mass of 2.3 kilograms and its temperature raised from 20 degrees Celsius to 80 degrees Celsius? And the specific heat of copper is 0.38 joules per gram Kelvin. Right. Joules per gram Kelvin. Okay, so what do we know here? What are the things we know? We know the mass of the copper. I'm going to use a different color. We know the mass of the copper. I'll use something that looks more copperish. The mass of the copper. See? The mass of the copper is 2.3 kilograms. Boom. The mass, that's all we need to know. And the change in temperature, delta T. for that copper is going to be the final minus the initial, so it's going to be 80 minus 20, and that's going to equal 60 degrees Kelvin. Great. What else do we know? We know the specific heat of copper. Pew. This is awesome. Specific heat of copper is 0.387 joules per gram degree Kelvin. Great. So the question is, when you turn it on, how much does the water pipes, how much do they heat up? How much heat is absorbed by the water pipe? Ah, okay. So the heat, we're looking for Q. So we know this equation, Q equals MCAT. We know this, we know this, we know that. So we can solve for Q. This is fantastic. The only problem I can foresee is that we're using kilograms here and we're using grams here. Let's change this into, well, we can either use, let's just use this as grams. Let's make that a little bit simple of a conversion for us. So let's change this into grams. So what's 2.3 kilograms in grams? Well, we know that there are, for every 1 kilogram, there are 1,000 grams. So this will equal 2300 grams. Great. So our mass is 2300 grams times 0.387 joules per grams degree Kelvin times 60 degrees Kelvin. So we're going to get as our heat. It'll just be in joules. You can see how the units cancel out. This is awesome. So it'll be in joules. It's going to be, with 2 sig figs here, 53 degrees. Oh, degrees. I said degrees. That's funny. And it's not 53. It's 3,000 joules. 53,000 joules. Cool. Now on to the last problem, number 2. A 2 times 10 to the second gram sample of water at 80 degrees is mixed with a 2 times 10 to the 2 gram water of 10 degrees Celsius. Assume that this is an isolated system with no heat loss to its surroundings. What is the final temperature of the mixture? This is something we're going to use our good equation that we just wrote out to find. You can see with the final temperature. Remember that the equation we just found right there? It was this. It was TF equals M1C1 TI1 plus M2C2 TI2 all over M1C1 plus M2C2. We know all of the C's. We know all of the M's. And we know the initial temperature of each sample. So if you do all that, you plug in every one of these values, the M1s, the M1, the C1, the TI1, you add all these up, you add those up, you divide them, you're going to get for a final temperature, you can check it yourself, you'll get as a final temperature, this is great, the final temperature in Kelvin is going to be 318. I changed everything to Kelvin. Notice that. 318 degrees Kelvin. Now, what is that in Celsius? If you did Celsius, it's going to be slightly different. But try to use Kelvin from here on out. Okay, good luck with all the problems. They should be similar to these two. That's all I have for now.